All right, so testing two different mics here. We all good? All right. So I guess I should make a couple of clarifications on the introduction before we begin. I'm pretty sure that Alex just drew a chain of causality whereby I can say that I'm responsible for Strange Loop. So I'm pretty excited to have discovered that, and can't wait to see my checks in the mail. The second thing that he implied a little bit was that there's a lot of opportunity to watch debugging happening on the product team if you work at Cognitect, and actually, you know, Datomic is really no bugs at all, so I don't know what he's talking about there either. But seriously, you know, in a closure audience, I really want to begin this talk with a rationale. Right? This is something that Rich has instilled as a value in this community, and so I put a lot of effort in having a good rationale, or trying to, and I'm going to have actually a multi-part rationale for this talk. The first one is debugging. Why should we care about debugging? And I think there's an obvious reason, because bugs. Right? We have bugs. That is a, you know, there are some estimates that have it that 50% or more of the cost of software development is actually tracking down the bugs later. Some of us, you know, work in environments where we get to run away and somebody else has to do that. So depending on what you do, you might not always feel that, but if you own something for a while, you come to realize that. That's pretty obvious. The second thing is that debugging is really a quite straightforward activity. And so, you know, Alex made used some sort of positive adjective to describe my amazing awesomeness at this, or whatever it was that he said. And the fact is, this is not hard to do, but people think it's hard to do. And so you can look disproportionately smart by doing it. And I am continually intimidated by the intellect and the achievements of the people in this room. Every time I talk to somebody, you know, they have some new area of knowledge that I didn't even know existed, about which they are expert. And so to be able to have something where, without the expenditure of neurons, you can appear to be very bright, is a valuable thing to have. And the final thing, and this is quite subtle, and I won't call this out as much in the talk. I mean, there's really I probably have about 8 hours worth of material corked up right now. But there's a follow-on strand which might lead to an interesting conversation, which is that understanding the way that I, and by proxy Rich, think about debugging might help you understand some of the aesthetic that goes into the design of closure and the process and the evolution of closure. It has come to my attention that sometimes people out in the world have more than one opinion about how to do things in the closure community, more than one opinion about how to do the getting started experience, more than one opinion about how to do documentation, more than one opinion about how to handle exceptions. We have lots of different ways of doing these things, and I'm not going to lay out here's one way to do it. Right? It's fantastic that there are multiple different ways, but I think that the scientific approach to debugging, when you adopt it, it influences what kinds of tools and practices you're going to reach for in other areas. And so that's very worthwhile of follow-on conversation tonight, those who continue on into office hours. Office hours will be held at, you know, whatever local bars, you know, stay open the latest. The second thing is a rationale for why to have me talk about this. There's a couple of reasons. I'm a closure screener. I am also Closure has a process which is not identical to every other GitHub project out there, as you may have noticed. And so I, in fact, push all of the commits and have for many releases now. I read every line of code that goes, I've read every line of code that went into closure since the 1.0 release. So I've seen a lot of things. I've seen many more things that didn't go into closure for various reasons. And I've seen things that were bugs and things that were thought to be bugs and not bugs. I also typically am the place of last resort in Datomic support. That doesn't mean that you're on fire if you call and I answer the phone, right? We're just rotating around. But I'm often the backstop on the hard problems. And so that has given me an opportunity to own a system for a long period of time and to observe bugs that we've had and bugs that other people have found that we had and bugs that people have had in their own systems that we've ended up helping them out with because of the support relationship. Also, I'm going to make a little bit of an appeal to authority here. I earned this gray hair. I've been doing this for a long time, and my hair was not gray at all when I first started debugging. So I'm pretty sure that, that most of this is directly related somehow. The alternate theory is that it has something to do with children. And finally, I am really lazy. I'm not the most terribly lazy person in the world, because you'd have to be competitive, right, to be that lazy. But I really don't want to work hard. And so I want to have an approach to solving problems that allows me on most days to close up my laptop at 5 o'clock and spend time with my children and have a tasty dinner and a glass of wine, whatever. Watch whatever HBO's most violent show currently is on TV and go to bed. So I'm lazy, and you can benefit from, programmers, we're all about laziness, right? We're all about finding tricks that will let us do things in easier ways. And so I think these all contribute. Then the question is, okay, we've talked about why debugging and why maybe I should talk about it. Why should we talk about debugging in a closure context? Well, Karen Meyer, one of my coworkers, pointed me at this thread on Reddit, I believe, and the text of this doesn't really matter, but you can sort of read it as, bloody, 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 blah, error messages, bloody, 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 blah. And it's basically the sort of beginner experience of closure. Right? A lot of people, when they are new to closure, particularly struggle with debugging their problems and figuring out what's wrong when something doesn't work. And so there's this long thread on Reddit where people talk about the problem. But this was actually the post that launches it, and it sort of captures some of the tone. And a lot of times people do things like, well, I had a problem and I got a cryptic error message. Or I was interacting with a dependency or a lining and plugin or something, and I didn't understand even where to start looking for my problem. Or I had a, air quotes, type error in my system that would have been trivially found if I was working in Java, and I now feel flummoxed. And so there are a lot of people whose experience of debugging closure is fraught or unpleasant. And my experience has not been like that. And I'm not saying that they're wrong and I'm right, but I'm saying that I might have some ideas that could make it pleasant for others. And so that's kind of an objective here. Now, before I go further, how many people in here, show of hands, have helped to develop tooling in the closure ecosystem? Right, worked on any kind of tool. So a lot of interesting tools in the closure ecosystem. There are a lot of interesting tools about editing, about debugging, about visualization of data, about visualization of flow. People have built a lot of different things. And this talk is not about that. And I want to make it clear up front that this talk is not anti-that. Right? I am a huge proponent of using tools. That being said, if you do a Google search for debugging, and I did this, the vast majority of the hits are about tools. Right? Overwhelming, well more than half of the Google hits. All the resources out there are about tools. And so I don't think you would be getting your sort of end-of-the-day keynote value add if I told you how to use tools, because there's a lot of good advice out there. And the thing is about tools, and hold on a second. That's interesting. The thing with tools is we're not directed by tools. Right? There is no TDD out there that stands for tool-directed development. We wield the tools, they don't wield us. And so when I think about debugging, I want to have a set of ideas in my head that give me direction. Or as that great philosopher of computer science, Yogi Berra said, if you don't know where you're going, you might wind up somewhere place else. This is one of the biggest problems when people start debugging a system, right? From my experience in a support perspective, what you discover, the first thing that happens when you start trying to help somebody with a bug, the first thing you find yourselves wanting to do is like, I really want to go back in time to when you first thought there was something wrong before you started doing anything. I want to go back to that point where you started acting before you had a plan, before you knew where you wanted to go. It's so often the case that, and I'm an advocate of being a self-starter. Right? So by all means, try things, but have a plan. And then finally, why would we talk about the scientific method? I had considered for a while that the approach that I used to debugging was the scientific method, but I had not, read the literature on the scientific method, past having had a science degree in college, and I had not read what people had to say specifically about the scientific method. So of course, I turned to Google to find out why I should care about the scientific method. And what I discovered is that the scientific method apparently is because rainbows. Which I have no idea why. I'm pretty sure that all the sort of the Edward Tufte people out there are just pulling their hair out. Like, what do these colors even mean? And so rather than use one of the pre-built graphics with the meaningless colors, I've made my own scientific method for debugging graphic. It's not that different from any of these, except it's got all the colors removed. So, because it's also sort of the limit of my ability to manipulate OmniGraffle. So what is debugging all about? Well, debugging typically starts with a failure. So a failure, and by the way, in Kahn's tradition, all the terms I'm introducing, I'm going to give you something from the etymology dictionary on them. Advice to future, proposal submitters: if you use 2 or 3 words that are slightly unfamiliar and make reference to etymology in your abstract, clearly that's something that is valued in this space. So what is a failure? A failure is a lack of success, or better, it's an omission of expected action. Right? I expected something, and I got something else. Now, as a result of this failure, you form a hypothesis. And a hypothesis is an explanation that's made without complete evidence, right? Without necessarily enough evidence to answer the question. Actually, maybe you don't even know whether you have enough evidence to answer the question. Maybe you do, but you just haven't sort of worked through the process enough. And that acts as a starting point for further investigation. Then, given that hypothesis, you perform an experiment, which is a test or a trial, and after that experiment, you make some observations, where an observation is active acquisition of information from a primary source. Now, in a good experiment, one of 2 sort of equally good things can happen. You can discover that the observation falsifies your hypothesis. So falsification is a deductive process. Using modus tollens, you say, I have a hypothesis. It implies there's something I should not see. There's some observation O that I shouldn't see. I run the experiment and I see O. Well, if my thinking has been rigorous and the hypothesis says, if this is true, then not O should happen and I see O, my hypothesis is now dead. And that's great, right? I know it's disappointing if you're trying to get grant money in the kind of regular everyday science, but in debugging, this is good news, right? We've now killed a possibility, and that's good. The other possibility is that the hypothesis is supported by the experiment, but maybe you still don't have an answer that's sufficient to let you say I've isolated it, at which point you need to do refinement. And refinement is removing impurities or unwanted elements, right? It's subtractive. So I have some sort of story here. Now my story may have to get bigger to remove elements, so I'm not actually saying the number of words in your hypothesis is going to go up or down. But the conceptual size of it is going to be focusing in on whatever the actual problem is. And then, eventually, and I'm not going to promise this happens after 2 or 5 iterations, but eventually you have a hypothesis. And the hypothesis is something that a theory is a hypothesis that has been validated by predictions. Now, this does not mean a theory is guaranteed to be true. It does mean, though, that it is true given all of the information we have so far. Right? So, and this is another place where people go wrong, and I see this all the time, right? I have 99 pieces of evidence in favor of this is where the bug is, and I have one little piece of evidence that flat out contradicts it, and I don't understand that piece of evidence. And so, well, 99 is pretty good, I'm just going to keep going, right? If you have that one little piece of evidence that says you're dead, right? You can't, and we get attached to our theories. That's the other thing. You get emotional about it. You're like, you know what? I really liked that theory, and look, it had 99 good pieces of evidence in favor of it. You can't do that. Now, it turns out, and sort of I get dragged into the sort of history of this, researching what other people have said about this for this talk. It turns out that there are all sorts of objections to the notion that the scientific method is how science actually gets done. Some of the objections are superficial or idiotic, perhaps. But there are more serious concerns as well. So one of the things that I studied in graduate school is Thomas Kuhn's book, The Structure of Scientific Revolution. And sort of there's all kinds of pithy ways I could unfairly summarize this book. But it essentially says that, that science is a little bit better than politics or religion in that you wait for people whose ideas are going to die out to die instead of actively going and killing them. Right? But it basically paints a pretty unpleasant picture that science is an extremely social process, right? And how could it not be, right? It's performed by people. And then, once you have this notion that science is a social process, it's opened up to what are the social priorities behind science, and you get all these moral challenges to science. So these hot button things, they change from decade to decade. One of the hot ones when I was in academia was the bell curve, right? This notion that we were going to use science, in air quotes, to sort of split the human race up into different groups and say, these groups are more intelligent and these groups are less intelligent. That's not the case. It's certainly not justified by the evidence. But these challenges are real, and here's the funny thing, right? Here's the good news, right? There's all kinds of stuff that I just said that we could have very heated debates about and get angry about, and in the context of debugging, we don't have to worry about any of that stuff at all. It turns out that debugging, if the scientific method is the measure of how science is done, debugging is actually more like science than science. Right? Science is hard. It's difficult to imagine how you could take that little process I just had and turn a crank on the side of it and come out with the theory of gravity or the theory of evolution, right? Or any of the other most important theories that people have ever thunk. But that's not what we're doing, right? That is not what we're doing. We're doing something that is far more constrained, right? And debugging is deductive, not inductive, right? We're not trying to come up with a grand theory of everything. Right? We have a grand theory of everything. It's called the software system we're running. We're trying to use that to prove some very concrete thing, right? This thing happened. Also, there's not a big political problem, right? There's not usually, in my experience, debugging in and of itself has not been politically fraught, right? There are people who are experiencing bugs and they want to see them fixed. And as the developers, we want to see them fixed. So we're not having these kinds of arguments. And there's not generally a lot of moral outrage, right? And there's not any kind of academic left saying, there is no real reality, so you can't actually, you can't actually prove that there was a bug here, right? There's none of that. So, seriously, this is really good news. So unfortunately, the scientific method may not be all that great for science, but it absolutely rocks for debugging. Now, having said that, we can drill in a little bit and we can start to use some more specific terms that are more about troubleshooting and debugging. So I'm going to replace the word hypothesis with cause. Right? We're looking for a cause. And the definition of a cause is an event preceding an effect without which that effect would not have occurred. That sounds awesome. Right? If I knew the cause of the problem, then I could eliminate the effect from happening. So I caused strange loop. Right? As we said earlier. So, so the problem with causes is that they're not sufficient. Right? Then cause, the universe exists. Right? If the universe didn't exist, this wouldn't happen. That's a cause, but it's not a very interesting cause, and it's not one that when we're debugging software, we're not in much of a position to do anything about. So you want to get from a cause to an actual cause. And an actual cause is the difference between the actual world and the closest possible world in which the effect does not occur. And we could go down the rat hole of getting rigorous about closeness, and I'm not going to do that in this talk. But I'll just be intuitive about closeness, right? If you have, this agglomeration of 5 things that all contribute, and with 4 of them it doesn't happen, and 1 of them it does, then that 1 is closer to being the actual cause. And so that's what the paring down process does. We want to start with an idea about a cause, and then we want to narrow down to an actual cause. And then we have this great word, fix. In this context, a fix is just the last experiment. Right? The first experiment is reproducing the bug. And then there are a bunch of experiments that are about hypotheses. And a fix is the last experiment. This captures a really important idea, which is if you haven't fixed it and run an experiment that shows it's fixed, you haven't really identified the bug yet. You may be strongly suspicious that you've identified the bug, but you haven't actually identified the bug until you've fixed it. So, I'm going to take this scientific method and I'm going to apply it in a really slapdash way to a problem. And I'm going to start with a problem that I grabbed off of Stack Overflow. This is a very tiny debugging problem. You can probably do it in your heads. So I'll show it to you. This is a question on Stack Overflow. Why is this partial not working? So I define partial join as the partial of closure.string/join with comma. Then I call partial join on foobar, and I get back the scary error message. Class cast exception. You cannot cast java.lang.string to closure.lang.ifun, and there's a scary number in it. So there's no way we can possibly figure out what the problem is with this terrible error message. So what should we do? Well, we have a lot of choices here. We could make error messages better, right? We could have an error message that says, oh, I see you were trying to make a partial with stir join, and that has this exact scenario. We could anticipate every possible scenario anybody could ever get into. And not to be unfair to error messages, we could go a long way towards having better error messages without being ridiculously over the top about it. Error messages can be made better. Sounds like a good plan to me. We could have better docs. Right? Maybe there's an answer to this problem in the documentation. We could use a debugger. In fact, in this case, it might be even that syntax highlighting and paren highlighting would have tipped you off as to where the problem was, and I didn't give you that. Maybe static typing would have helped. Right? In fact, static typing would have helped. Right? You can imagine a scenario where static typing would have solved this problem. Using some sort of schema and schema validation would have helped. And in fact, this one's so easy that you might have stared at it and just known what the problem was. So all of those things are useful. And all of those things should be part of your toolkit, except for maybe staring at it. Right? That one's actually really quite weak, and we'll come back to that. But the important thing to realize here is that science is more general purpose and requires less on hand to do than any of these other things. I'm going to say that again because it's so important. Right? Science is more general, the scientific method here, not science. Let's say the scientific method, or we can even be, what is it that the academics say? Hypothetico-deductivism. Right? Let's just stick with scientific method. The scientific method is better sauce than these other things because it's more general and because it doesn't require anything to exist in the world except your brain before we go in. So let's try that. We're going to go down this road, and I'm going to do this, as I said, in a really slapdash way. My hypothesis is going to be, well, look, there's only 3 things here. Why is this partial not working? Well, join doesn't do what I expected. So it's a very fuzzy hypothesis. Or partial doesn't do what I expected. Or def doesn't do what I expected. Right? It has to be in one of those 3 things. Right? Those are the only 3 things there. It's a very small problem to check. And so the experimental approach to this, I will propose a heuristic for small problems like this, which is you should do a bottom-up check from the REPL. Right? Pick the form that's at the bottom or that's on the inside and check that. And in this case, we're done. Right? I checked the very bottom form here. The bottom form was closure.string/join, comma, which returns comma. That seems like almost certainly wrong because if it was just going to return comma, I could have just passed in comma to begin with. And then when I look at the next one, partial join, if we substitute in the result of that, right, in the original form, we're now partialing over comma, which is using comma as a function. So by applying this, now I got lucky this time. I might have had to do 3 little things at the REPL to figure this out. But I got lucky, and I only had to do 1. So weak science is stronger than strong tools. In this case, I had a poor problem statement. I really never got clarity on my problem statement. I had really poor hypotheses. Each one of my hypotheses was that was ouch, or that was ouch. Right? Those are not very specific. My experiments didn't even really have stated goals. Right? I just sort of took this heuristic approach. And I didn't have much domain knowledge. Right? Or hypothesized that a beginning closure programmer doing this didn't have to have much domain knowledge to figure it out. So, of course, at this point, I've stacked the deck in favor of the scientific method by picking a trivial problem. A trivial problem doesn't matter what you do, right? Any one of the approaches would work, so it hardly matters. So now we need to talk about hard problems and what it would be like to do the scientific method well. So what do we need? We need to do each of those steps way better than we just did. We need clear problem statements, we need efficient hypotheses, we need good experiments, useful observations, and we need to write things down. I'll start with problem statements, right? The antithesis of a good problem statement is it didn't work. Right? It didn't work is hiding everything behind pronouns. That's no good. Right? What you want is the steps you took, what you expected, and what actually happened. This slide right there, that's worth $100. Send me your checks. All right, this is not a hard thing to do. This is not harder than, and in fact, sometimes saying this actually causes you to realize what the problem was. Going from the exercise of verbalizing it didn't work, from the exercise of verbalizing, I stepped away the car and it started to, oh, right, I didn't put it in neutral, whatever. So problem statements, there's a lot. As I said, I have 8 hours of material. There's a lot we could say about problem statements. This is all you're going to get right now, but this is an order of magnitude better than it didn't work. So start with this. The next thing you want to do is to, and I am going to Give me 1 second. Why? I don't know why it's not working. I'm going to debug this. I have a live performance now. So my hypothesis is actually it's Keynote, right, which is just terribly painful. So I want, oh well, fine. I'm not going to tell you. How many people remember this guy? Yep. I mean, it's Casey Affleck, but it's the Malloy twins from Ocean's 11. And there's this great scene where they're playing 20 questions. And they're playing 20 questions, and he's like, am I alive? Yes. Am I a person? Yes. Evel Knievel. Damn it. Right? And it's a joke on an idea that we all know. It's like the opposite of what you want to do. Right? It's what my 5-year-old does when we're playing 20 questions. He's like, okay, we're going to play 20 questions. And he looks at me and goes, am I a tall oak tree? It's like, no, you don't want. We all know what we need to do here when we're forming a hypothesis, right? You want to form a hypothesis that ideally carves the world in half. And so it turns out that the naming around this is contested. Right? Most of the time you hear people say this is divide and conquer, but if you ask an algorithms person, they would say that's actually not it. Because in divide and conquer, you go down both branches. And so they want to call it decrease and conquer, which I think kind of sucks. Because it doesn't, I mean, decrease and conquer could be a linear time thing, right? You could decrease by 1 every time. And the important characteristic here is proportional reduction. Right? I want to take the space of where the problem is, and I want to reduce it by ideally half. But as you know, if you've done any algorithm analysis, right, if I can get rid of 10% of the possibilities on every step, I'm going to have the answer really quickly. Right? That's only going to differ from getting rid of half the possibilities by a constant factor, the number of steps that I have to do. So the question is then, how do you take the space of I don't know what went wrong and turn it into something that cuts the world in half? Well, this is going to require domain knowledge, right? There's no two ways about it. Having said that, it does imply that you should be super cautious on your initial step if you don't have much domain knowledge. Right? If you don't have much domain knowledge, it's possible that your initial step leaves out of the entire universe of possibilities what the actual problem was. And so, having said that, everybody knows where to look for their bugs. Right? If I showed you your application stack and something just stopped working, right? How many of you are going to guess? Right? How often, right? It just doesn't, right? How often is it physics? It's pretty rare, right? Physics is not usually, I mean, sometimes it is, and that's exciting. But, and I have to say that on every open source, project I've ever worked on, you get bug reports, and some of them are bugs, and you fix them, and some of them are not bugs, and some of them are bugs in something underneath you, right? We've never had a closure bug report that we had to forward on to physics, right? There haven't been any of those. And in fact, very few even have to do with JVM, much less OS operation. And you could make other stacks like this. There's a whole conversation we could have about sort of developing a notion of what the possible space is and where you can go in it. But my point is you don't have to be that good at it anyway. Right? As long as you can get rid of some proportion of the possible causes with your experiment, you're going to quickly find the answer. Now, what is a good experiment? A good experiment's reproducible. Right? You start by reproducing the bug. It's driven by a hypothesis. Right? People say they're experimenting when they're just trying shit. Right? That is not hypothesis driven. You have an idea, this is the case, and then you have an experiment that provides more information to help you refine that idea. Also, experiments are small, and when you're making changes to a system, you change one thing at a time. Right? Because if you change two things, now you just have to go back to figure out what the impact of that was. When something changes, right? You haven't actually gained information. So I'm going to give you a quiz on this. If you have a bug, let's say you want to report a bug in your own app, right? And you're handing it off to another member of your team to help you look at it. Which of the following things should not be in your repro case. Closure test, cursive, prismatic schema, Midge, Potemkin, nREPL, Leiningen plugins, core typed, test generative. Right? Unless you're actually, unless you think the bug is in one of these things. With one of these, it really stands out as, boy, you really wouldn't want to have that in a repro case. And the answer is it's a trick question. You don't want any of these in your repro case. Unless your theory is that, the shopping cart on my system doesn't work when I'm developing inside cursive and using closure.test, then your repro case shouldn't have anything to say about cursive and closure.test. And Colin and other people will thank you for that, because he doesn't want to get bug reports about cursive that are about that kind of thing either. So it's incredibly important to remove things that do not contribute to your hypothesis statement. And it's a freebie. Right? I was saying earlier that you have to have this mental model of the universe to allow you to narrow down the things that aren't it. Right? This is a freebie. Right? In your bug, these things are not it. So start by taking them out. Make a really tiny thing that shows the problem. Now, when you're making observations, what's that all about? Well, one thing you need to do is you need to understand all the outputs. Right? If your system has outputs, right? If your system has 4 or 5 outputs that you understand, and then it has one that's unrelated to your current problem and you don't understand it, brakes screech. Right? If you don't understand it, how do you know if it's related to your problem or not? So you need to understand the outputs from your system, and you need to be suspicious of correlations. Where's the code? It's in the bug. It's in the last 5 lines of code you wrote. Right? Quite often. And so if anything correlates with with a failure appearing, then you want to suspect that. And in order to make observations, you need good tools. You need debuggers. You need logging. You need metrics. All the kinds of things that basically all those things give you more outputs. Right? They turn things that are black box into things that are white box. And it's amazing that we have this inversion that when you do a Google search for debugging, more than 50% of it is about just this one sub-bullet of one sub-point. It's important, right? You need to have tools. And in fact, there are more things that tools can do than just this, and we'll talk about those later. So I'll give you another example. And while I was writing this talk, I had several things that happened to me in the course of the week. So this is one that happened to me last week. I was working on a Closure app, and I got this error message in the log that was completely unrelated to my problem. Right? My problem had nothing. So logback is the configuration file for logback, which is one of the Java logging things, which we're also happy that Java did such a good job with. And so I get this message, and I'm having this cryptic problem in a subsystem that I'm working on. And I know this can't be it, because it just has to do with logging, except that actually this was it. Right? So it turns out that after 2 minutes looking at the problem, I said, you know what, before I think about this problem, I'm going to go run down what this logback thing is about, because I want this to be clean. Well, logback occurs multiple times on the class path because some library, because of a build problem, had been copied into a lib directory twice at 2 different version points. So I had foo.bar version 2.1 and foo.bar version 2.2. Now, what the JVM helpfully does in that scenario, without further configuration, is if those things have overlapping but not entirely union set of named things in them, you can get some of them from one and some from the other, and they're not compatible with each other. And it can lead to all manner of errors that are absolutely cryptic, which is exactly what happened. But by tracking this down, I was able to say, you know what, I saved myself all that time, and it would have been, even using the scientific method and trying to sort of bisect towards the problem, it would have taken a while from the symptom to come up with a better cause to investigate than the one that was standing in front of my face. Write things down. This is the single most important piece of advice I'm going to give in this talk. Write things down. Write the problem statement down. Don't say it, write it down. Write every hypothesis down. Write what the experiment would show. Write why the experiment makes sense. Write a justification for the experiment before you run it, and write down your observations. And this is something that we all know sort of intuitively. Consider the game Mastermind. So in the game Mastermind, the colored pegs down at the bottom represent a code that the player is trying to guess. And the colored pegs across the top represent past guesses. And then the little red and white pegs represent information, feedback that you've gotten on your past guesses. So if you view this as a scientific method, right, you have a series of hypotheses about what the colors are. And you're getting feedback from an experiment, which is the human player is scoring your guesses. we don't have to talk about exact scoring if you can't remember how Mastermind works. That doesn't matter. The thing that's dominant here is that doing your experiments without writing things down is like playing Mastermind like this. Right? You're saying that you're going to keep in your head the entire state space of all the previous things you've tried, and even the one try you're currently on, you're going to hold in your head. So I'm sure you can barely see one of those through my color there. And the thing is that not writing it down, right? You might think that of the 7 deadly sins, that's sloth, but it's actually not. It's hubris. It's amazingly arrogant not to write things down. Because basically what you're saying is, I'm such a badass at solving problems that I'm going to solve the meta problem of keeping track of everything in my head just to show off. When that's actually probably a harder problem than the debugging that you're doing. And people do this all the time. It's staggering. Okay, everything I've said so far probably could more or less apply to the use of the scientific method in a lot of different domains. And because we are here at a software closure conference, I'm going to give you some software-specific advice. The first piece of software-specific advice is something I was reminded of as I was reading through the literature on debugging and what programmers have said about debugging in the past. And I usually don't say mean things like this, and it's going to come off a meme, and I can't help it. Don't use C. Right? I mean, the history of debugging is just riddled with, oh my God, this thing has so many pitfalls and traps in it. And it's not that C is bad. I mean, we could have a separate conversation about it. It's that this is not a level of abstraction you need to be working at. Right? And sometimes it is. Right? And if you have a domain that's like, it would be impossible to do this in Java or Clojure or Python or whatever, then you can use C. But boy, you shouldn't reach for that as the default tool in 2015 in most domains. Second piece of software-specific advice. The failure is not the defect. Right? The failure is not the defect. And the way this comes up the most often in software is assuming that the exception has anything to do with the actual problem. I mean, it does have something to do with it. That's how you know. Right? But that it's in some way directly translatable into the problem. So I'll give you an example. We had a datomic system that had a large query, high CPU utilization, and an illegal state exception in Hornet queue. So your first guess is, wow, illegal state exception. Hornet queue must be broken. Well, let me just tell you, Hornet queue is not broken. Hornet queue is a pretty awesome piece of software. I've had fantastic interactions. Datomic has had Hornet queue in it from the 0.0 days. I've had fantastic interactions with the Hornet queue team, and the only time that working with those people that we ever got to the point where we tracked a bug down to the point where it was underneath Datomic and in Hornet queue, it actually was underneath Hornet queue and in Netty. Right, which is pretty unusual, by the way. You don't find those kind. I mean, this is a show-stopping Netty plus SSL doesn't work in this scenario bug. So pretty darn unusual. So this was not this bug, and I'll just tell you. I'm sort of giving you a little bit of unfair advanced information. The answer was not it's Hornet queue. And there's another important philosopher of debugging who can really help us out here in a couple of steps, and that is House. So House says it's never lupus. Well, in closure programming on the JVM, we have a kind of anti-lupus, right? We have the thing that it always is, but it doesn't look like it at first. And the thing that it always is garbage collection, right? The actual bug is always garbage collection. Just as in House, it's never lupus. In Clojure and in Java, it's always garbage collection. And there's several reasons for that. One is most applications are not designed to deliberately induce out-of-memory errors. Because they're not designed to deliberately induce those code paths are not checked very much. So you're in kind of uncharted territory. The second one is out-of-memory can happen anywhere. So there's no line of code where you can like, oh, look, there's the critical section where memory doesn't possibly run out. Right? You can't do that. Also, out-of-memory can appear as almost any other exception. Because once something fails to allocate over here, you can get a cascading series of reactions where the actual exception that's reported back is radically different. Finally, well, not even finally, sub-finally, when you get close to out-of-memory, you get a radical change in thread scheduling as the GC thread is running all the time. And all of a sudden, things are happening in orders that they never happen in everyday life. And so all those race conditions that would normally take your system 2,000 years to expose by accident, all of a sudden it takes them 2,000 seconds to expose by accident. So lucky you. Thanks, garbage collection, for helping us find those race conditions. And finally, out-of-memory related problems tend to cascade. So always be suspicious of memory when you're having problems in a garbage collected environment. Now, another piece of software-specific advice is to read the entire fracking manual. And so the thing is that a bug, almost by definition, starts out as an unknown unknown. Right? If you knew more about it, you'd already be well on the way to fixing it. You don't know what's wrong, so you don't know which part of the manual you need to read. And this means that if you want a set of docs that are good for debuggers, that set of docs ideally is short and specification-like. Now, this goes against other objectives. Right? Short docs may be very difficult to consume. They may not be very narrative. They may not be very tutorial. But they are a good place to say, you know, if I have to read the whole thing, I would like for it to be 50 pages long and not repeat itself. If I want to learn in a more tutorial kind of environment, I'd like for it to be 1,000 pages long and repeat itself in various ways and anticipate problems that people have every day. So good docs for debuggers are specs. And we'll go back to the partial problem again. So if instead of doing experiments we had chosen to read the docs here, we could have pulled up the doc string for join, and we would have seen that join has two arities. And the first arity takes a collection, and then it returns a string of all the elements in that collection. Oops. So one step plus experiment would have identified this problem. One step plus reading the docs would have identified this problem. Right? Would have been the first thing you found when you went to look for it. So let's take some of these ideas back to this more tricky debugging problem that we encountered. And that is this large datomic query, high CPU utilization, illegal Hornet state, illegal state exception. And now I'm going to give you one more really piece of interesting information. It happens on Cassandra in production, but not on H2 in development. So what should we do right now? If we're going to apply the method, what we need to do right now is look very suspiciously at that last sentence. Is that last sentence an observation, a hypothesis? What is it? It's actually not really anything. Right? It doesn't have a subject. Right? It's a sentence without a subject in it. So there's some sort of amorphous it that happens on Cassandra and not on H2. So let's try to define that it a little bit. That certainly sounds suspicious. So let's make the smallest possible thing that could show us that. So we'll create a test environment with the same data that production had. And then we will run a little file that we're going to write, which is going to be 10 or 15 lines long, test.java with a datomic peer. And that's just going to come up, and it's going to perform the problem query in a loop. And if Cassandra or datomic or Cassandra plus datomic is trivially broken in some way, we're going to see that there. And then we can run the same test again against dev and not see that there. And now we have eliminated an entire universe of complexity. Right? All of the application code that was in play, all of the tools, all of the third-party dependencies, all that other stuff has been mechanically eliminated. Well, so we did this, and what did we learn? The problem happens on Cassandra. This is our statement. It happens on Cassandra, but not on H2. So we create the trivial repro, and it happens with Cassandra, and guess what? It's lupus. So it turns out that this query was just using more memory than the JVM had and had no chance of winning. And so then it's like, well, that's pretty suspicious because it's not at all obvious why Cassandra would be such a memory hog and use a ton more memory than H2. That seems really, Cassandra has a good reputation. Why would their driver, be messed up like that? Well, stop hypothesizing ahead of the evidence. Let's go test H2, the dev mode storage, and guess what? The trivial repro happens there as well. And that leads me to the other important observation that we get from House, which is that everybody lies. Right? It turns out that it was not the case that the Cassandra and the H2 behavior were different. It turns out that there was a miscommunication about what had been tried. And by the way, never attribute to malice what you can contribute to accidental miscommunication. This is not lying in the sense of covering up your drug use, which is always what it is on House, right? This is lying as in saying a statement which turns out not to be true. I'm having a lot of trouble teaching my kids not to always call that lying. Right? Any statement which turns out not to be true later or turns out to be slightly mistaken, they're like, Daddy, you lied. Like, actually, we tend to use that word to imply malice. So this is the non-malice kind of lying. This is the, go back and double-check statements. And again, going through the exercise of reproducing it. I mean, imagine how much fun we would have had if instead of doing that, we had sat across a conference table and the datomic team had pointed at the Cassandra devs and the Cassandra devs had pointed at the datomic devs and said, you guys have messed up somewhere because this works in other contexts. Right? We didn't even have a problem statement, until we did that. Now, the final piece of advice I'll give you as software developers is that debugging is fundamentally a search operation. We should ponder that a little bit because this is something we actually know how to do, right? We actually know how to write algorithms that do it. So instead of limiting our thinking about debugging to the ability to see things or stop things, why don't we write programs that do this job that I just described, right? Implement the scientific method in code. Make something that automatically generates a hypothesis and then automatically runs an experiment. And some of you may have done that in a small way using git bisect. Right? Git bisect is actually partial automation of the scientific method. Right? You write a little program that's going to test for something, and then Git will bounce back and forth, cutting the world in half every time until it finds the boundary at which your test changes. Right? That's automating the experiment part, and we have the set of possible world states already given to us from Git. Well, this idea is well suited to being taken further, and so I'm going to give you your first maybe ClojureCon call to action this year, which is go and read this book, Why Programs Fail, by Andreas Zeller. And in particular, there's a lot of ideas in this book that have now become standard practice, so there are chapters you can skip. But in particular, read chapters 5 through 7 and chapters 11 through 14, which actually lay out algorithms for doing automatic debugging of programs. And so what they're doing is modeling the entire state space of a broken program and the entire state space of similar programs that don't exhibit the failure, and then shrinking the difference in those state spaces. Do we know how to do shrinking in the Clojure world? We're pretty good at that, right? We have test.check and test.generative. There are algorithms for this. So I would love to see, maybe at Clojure West or maybe at ClojureCons next year, somebody giving a talk about taking the ideas in this book and realizing them in Clojure. Most of the ideas in the book are demonstrated with Python code, and I don't think, and Python's a great language, but we should not let them have all the fun. Right? This is a problem which is well suited for Clojure, because as you might imagine, one of the places where this gets complicated is I can just glibly say the entire state space of a succeeding application and the entire state space of a failing application, but how are you actually going to capture that? Well, that's a hard problem, but it's easier in a language that doesn't have very much state. Right? So to the extent that it's possible at all, right, in a ball of mud Python program, it ought to be a lot easier to do in a Clojure program. And oh, by the way, having a language that models code as data and passes everything around as data, we are uniquely in a good position to implement these kinds of algorithms. So that's the software specifics. Work at a high level of abstraction. Remember the fault is not the defect. Remember that GC did it. Read the manual twice. Don't trust, because people lie, reproduce. And let's go out and automate some things. And I've been told that 6 bullets is too many to remember at the end of a long day, so I'll make that even simpler and say, let's back up and talk about science a little bit. It's really easy. Know where you're going, right? Remember Yogi Berra. If you're heading into a particular direction, you have a much better chance of getting there. And then make well-founded choices. This is where developers, both beginner and expert, make the most frequent mistakes. They're under pressure and something's not working, and you say, and we've all done it, and you say, you know what, I'm going to try this. Stop and ask yourself, why should I try that? Stop and ask Plushie Cthulhu. You don't even have to talk to another person. You can say, Plushie Cthulhu, I have this idea about what's going wrong and why my keynote presentation didn't do what it was supposed to do during the middle of the talk. Maybe you and I can sit down afterwards and I'm going to talk you through, I'm going to give you a hypothesis. The effort of doing that and writing it down, that's the final thing. Once you've decided you're going to take any kind of action, justify that in writing first. Right? Those 2 steps, making good choices and writing your steps down, are going to turn a haphazard random walk around a problem into a directed, focused cruise to an easy solution and an early night relaxing at the bar with your friends. Thank you very much.